Okay, so now this is your chapter number 10, vapor power cycle. So you have to follow your book as well. So this is from your book, which is Thermodynamic Approach by Singer. Okay, so first I will previously I will define just quickly that there will be some type of cycles which you have to study in this course. Okay, so basic thing is that there was some type of cycle which we are going to study in thermodynamic course. The first one is your heat engine. Okay, so but do not confuse that term engine with that it is related to your automobile engine. Okay, so it is related to all type of power producing devices, whether it will be a steam power plant, whether it will be a any other coal producing plant or coal power plant, or whether it will be some sort of another nuclear plant. Okay, so this will be related to heat engine. So any power plant that are producing some type of work comes under the heat engine category. Okay, and so broadly we just define that all our power plants, all our power producing device work on the Rankine cycle. Okay, so but there will be other type of cycle as well, which is called a gas power cycle as well. We also go have to study in this lecture in later lectures as well. And under that gas power cycle, there will be a Brayton cycle. Then there will be internal combustion engine cycles. Okay, there will become under this domain Otto, diesel, Stirling cycle, and then there will be a refrigeration and heat pumps and air conditioning. So right now, just I will define you that what is different between heat engine and gas power system and gas power cycle. So the main difference between the heat engine and gas power cycle is that whenever you are analyzing the gas heat engine, so you always remember that your working fluid is always in liquid or vapor state. Okay, so mean it will always remain in liquid and vapor state throughout your power producing cycle. However, so it's mean that sometime it will be in the liquid state, sometime it will be in the vapor state, and sometime it will simultaneously in the liquid and vapor state. Okay, so this is the working principle of Rankine cycle or heat engine cycle. However, in the gas power systems, your working fluid is always remain in the gaseous state. Okay, always. Okay, so this is the difference between heat engine and gas power system cycle. However, internal combustion engine I will define in later lectures, but you just have a quick overview that in internal combustion engine we call as a air standard cycles. Okay, so this is the difference. So right now you just have the knowledge that because in this lecture we are going to analyze heat engine only. Okay, so the working fluid will be liquid and vapor or liquid plus vapor. Okay, so this is the main difference. So now going to forward. Okay, so first you have the knowledge about Carnot engine or Carnot cycle. Okay, so what is the Carnot cycle? So Carnot cycle is one of our idealized cycle. Okay, you all know that it has a maximum efficiency. So, but here the question is, if Carnot cycle has a maximum efficiency, so why we are going to study different type of cycle and why we have to build different type of cycle? So why we do not use our steam power plant, power producing device on the Carnot cycle and produce a maximum efficiency? Okay, so this is the best possible solution in order to gain a lot of work by our steam power plants. So, but there are some limitation of Carnot cycle. However, in Carnot cycle, you also see four parts. That is, first is the boiler one, second is the turbine, there will be a condenser, there will be a feed pump, and all these four parts are similar in all the cycles. Okay, either it will be a Rankine cycle. Rankine cycle, you also see these parts that it comprises of these four parts. Okay, and it makes a cycle. However, the difference between Carnot cycle and Rankine cycle is based on some limitation. Okay, and that limitations I will explain to you that what are the limitations why we are not using Carnot cycle in our steam power plants. Okay, so first thing, you already know that how to build TS diagram. Okay, so we have built the TS diagram and just mark it the processes which are happening in the Carnot cycle and states 1 to 2, 2 to 3, 3 to 4. So one of the main thing is that the process 1 to 2. Okay, so if you see that it is an isothermal process in the Carnot cycle. Okay, so whenever it will be isothermal process from 1 to 2, okay, it's mean that your this point T2. Okay, so T2, which is the T highest point. Okay, you can also call the highest temperature. Okay, so highest temperature is less than T critical temperature. Okay, so where is your T critical? So here it is T critical. Okay, just at the dome. Okay, and if your T highest is less than T critical, it's mean you are turning limits to the thermal efficiency of your cycle. Okay, which means you are producing less, you are getting less efficient cycle. Okay, if your T highest is less than T critical. Okay, so this is one limitation that why we are not using a Carnot cycle in our daily steam power plants or any other type of working devices. Okay, second thing is that the process 2 to 3. Okay, the 2 to 3 is an isentropic expansion process due to decrease in temperature. Okay, as you see that 2 to 3, there will be a decline in temperature and the highest moisture content in the steam turbine. So this 2 to 3 is your turbine. Okay, turbine produce a major source of erosive wear of the turbine blades. It means that your turbine blades easily disintegrate and it will be and that will turn into the wear of your turbine blades as well. So which means that we do not want that our turbine blades wear so quickly. Okay, so that's why the process 2 to 3 is also making an issue in Carnot cycle. And then the most importantly is your 4 to 1. Okay, if you see that 4 to 1, okay, which is your compressor one or the pump one, that point lies in your, okay, first thing is that I think all you have the knowledge that this is your compressed liquid state, this is your superheated state. If we are going on the dome, okay, so these are the saturated liquid, these are the saturated vapor, and inside this is liquid and vapor two phase. Okay, so point number 4 lies in your two phase region. Okay, and it is not practical if you just read this line. It is not practical to design a compressor which can compress two phase liquid. Okay, so here we are going to compress the two phase liquid if in the Carnot cycle, and which is not practical to design such type of compressor or such type of pump which can compress two phase liquid. So these are some limitations that why we are not using Carnot cycle in our steam power plants. So now coming to the vapor power cycle. So this is how your vapor power cycle look like. Okay, so as you see that real vapor cycle, there will be a lot of equipments that are seen over there. So but the main components are your boiler, your turbine. Okay, boiler where you are going to input your heat, turbine which are going to produce your power. This is the heat sink. Then there will be a pump. Okay, and rest of the things are connected to these components are connected to your cycle as well. Okay, so there will be a cooling tower where you are going to reject the heat. There will be a stacks. Okay, so but for analyzing the vapor power cycle, we just have to analyze these four parts. Okay, right now. So our main interest in these four parts. So this is your vapor power systems look like. Okay, so first thing before I start with the Rankine cycle, that how the Rankine cycle have to be look like. So you have the knowledge about TS, TV, and PV diagrams as well. Okay, so the main thing here is you have the knowledge about that this is the compressed liquid region. Okay, and this line is your saturated liquid line. So if your point lies on this line, it will be a saturated liquid. This is your critical point. Okay, and then there will be a saturated vapor line. Okay, so here it will be in the vapor state, and this is your superheated vapor region, and this is your two phase region, which is liquid and vapor. Okay, so you all have the knowledge that what is the saturated liquid, the liquid that is about to vaporize. Okay, so this is your saturated liquid, and what is the compressed liquid, which is forced to be a liquid. And second thing is it's come from your thermodynamics one course, so there will be nothing new in this. Okay, so saturated liquid and vapor region, which lies in your two state one, mean the liquid and vapor phases coexist at this point. Then there will be a superheated vapor, the vapor that is not about to condense. Okay, so that is not a saturated vapor. That is still not a saturated vapor. So saturated vapor lies on this point. Okay, so if it any point lies on your saturated vapor line, it will be a saturated vapor. And other if points lies in this area, it's mean it will be a saturated vapor region. Okay, so this is just a quick review. Okay, so now coming towards the Rankine cycle. So this one showing here is your ideal Rankine cycle. Okay, so again, the main components are your pump. Okay, so you have to give some work to your pump at state 1 to 2. Then from 2 to 3, there will be a boiler. Okay, so where you are going to add some heat in the form of any type of thing, solar energy, either burning coal or either burning fuel or any other nuclear type of fuel. Okay, at point 3 to 4, there will be a turbine where you are going to produce some work. Okay, so this is your work turbine. Okay, then there will be a 4 to 1. This is your heat sink where you are going to reject your heat. Okay, so this is your Q out. So these are the four major components for the Rankine cycle, which is the ideal one. I will explain you what is the difference between ideal and the real Rankine cycle, but that will come in your later lecture. So right now you are focusing on only the ideal cycle. Okay, so this is your ideal cycle. Okay, so this is how it's look like. Okay, so first thing you have to notice that for the process 1 to 2, 1 and 2. Okay, so this is your turbine, and in turbine, it is the isentropic expansion of fluid through the turbine from saturated vapor to condenser pressure. Okay, so main thing is that in your turbine, it will be an isentropic expansion process. What does this mean? That why if there will be isentropic expansion, it's mean that your turbine is producing maximum work. Okay, if there will be a isentropic expansion. Okay, the reason behind isentropic expansion is if you see on this figure here, okay, you see that there will be a dotted line along your turbines. Okay, so what does this dotted line show? This dotted line show that your turbine is highly insulated. So mean that your um, energy, there will be energy losses is equal to zero. Okay, so there will be no energy losses, mean that your turbine is producing maximum work, so it will not lose any energy while producing any work. So that's why, and that is happening because of the isentropic expansion process. Okay, the second thing is 2 to 3. So where is your 2 to 3? Okay, so this is your 2 and this is your 3 point. So here there will be a condenser. Okay, and at the condenser 2 to 3, it will be a constant pressure process. Okay, constant pressure mean, so whatever the pressure will be at 2 will be same at pressure at the point 3. Okay, so this is your constant pressure heat rejection. Okay, so then there will be a point which is, okay, so now looking for the 3 to 4. So where is the 3? 3 point is this one for your pump. Okay, so at 3 and 4. Okay, at 3, 4, there will be isentropic compression of the fluid. Okay, to compress liquid. What does this mean? That there will be isentropic compression. Isentropic compression mean that you have to supply minimum work to your pump. Okay, so we are giving minimum work and producing maximum output from your turbine. Okay, so this is mean by the isentropic compression and isentropic expansion process at your 1 to 2 and 3 to 4. Okay, so then another important thing is that process number 4 to 1. Okay, so this is your boiler. Okay, so if you, we can just notice over there. So this all the area is your heat addition process at constant pressure. Constant pressure mean that whatever the pressure at 1 is equal to pressure at 4. Okay, so this is how your Rankine cycle look like. Okay, so I will explain you that how you can find these pressure terms and how you can analyze the thermodynamic cycle of your Rankine cycle. Okay, so the main important thing is that in any question which is coming in the later lecture, we have to find out the efficiency of our cycle. So for the efficiency, we already know that it will be a ratio of your total work by the cycle and your Q supplied. Okay, and your W cycle is equal to the work produced by the turbine and work produced by the minus work produced by the pump over your input heat. Okay, so this is how we can analyze the efficiency. So if I ask you that to find out the efficiency, you have to find out the work done by turbine, work done by power by the pump, and your supplied heat. Okay. Okay, so this is your ideal Rankine cycle. You already, I already explained that there will be from 1 to 2, there will be isentropic compression. 2 to 3, it will be a constant pressure heat addition. 3 to 4, isentropic expansion. Okay, where you are producing work. 4 to 1, it will be a constant pressure heat rejection. Okay, so now coming towards the Rankine cycle analysis. Okay, so in order to find out your work done by turbine, work done by pump, so you have to analyze your Rankine cycle by using energy balance equation. Okay, so this is your energy balance equation. What does energy balance equation says? Okay, so this is your energy balance equation. Energy balance equation says that all your energy input, energy output is equal to change in enthalpy, delta H. Okay, so this is our energy balance equation. So in order to analyze, for example, I want to analyze for my pump. Okay, if you see that for pump, where is the pump? Pump is installed at point number 1 to 2, between point 1 and 2. Okay, as you know that for the pump one, okay, so there will be a no heat involved in it. Okay, so all our Q terms is 0. Okay, and what we are doing is we have to supply uh, work to our pump. Okay, so W out is 0, and this is HE. HE is defined as your enthalpy at exit point. Okay, and HI is your enthalpy at your inlet. Okay, so what is your enthalpy at the exit point? H2. Okay, H2 is your enthalpy at the exit point. H1 is the enthalpy at your inlet point. So the pump in will turn into H2 minus H1. Okay, so enthalpy is because we are going to turn this equation in terms of enthalpies so that it will be easy for us to analyze the system. Okay, so we have to find out enthalpy at each point, then we can easily find out the efficiency and work produced by our pump and work produced by the that work supplied to the pump and work produced by our turbine. Okay, then another form of
प्रेशर टेम्परेचर से टेबल के जरिए पता चलेगा
जी आपको थर्मोडायनेमिक्स टेबल के जरिए पता चलेगा लेकिन दैट आई विल टेल यू हाउ टू फाइंड आउट दैट फ्रॉम थर्मोडायनेमिक्स टेबल व्हिच आर कमिंग इन आवर लेटर सेक्शन. Okay, so then another form of equation for the same pump is the work supplied to the pump is your specific volume into P2 minus P1. This comes from your thermodynamic 1 course. Okay, so it will be not new, but here the important thing is that what is this specific volume? This specific volume is at your state 1. Okay, and pressure 2, if the pressure 2 is known to you and pressure 1 is known to you, you can easily find the work done by now work supplied to your pump. Okay, so this is how you can find it. Okay, so then coming towards our next part. So your next thing is your boiler. Okay, if you see that your boiler is installed between state 2 and 3 and you are going to supply some type of energy to your boiler, okay, in form of anything. Okay, so again going to your energy balance equation, so you can see that for the boiler one, all over there will be no work done in your boiler. Okay, so work terms are 0. Then again you are not going to reject some heat from the boiler, so Q out is equal to 0, and then Q in is left, and then there will be a He minus Hi. So He is equal to H3 and Hi is equal to H2. So here the equation becomes Q in is equal to H3 minus H2. Okay, clear? Okay, then going towards the turbine section, if you see our turbine. Okay, so turbine is installed at point number 3 and point number 4. Okay, so point number 3 and point number 4 mean that okay, so what we are doing is that Q is not available in turbine section, so Q terms are 0. Okay, and we are going to produce some work. Okay, so mean there will be a W out term. Q supplied is equal W supplied is equal to 0. Okay, and there will be He minus H1. Okay, so minus W out is equal to H4 minus H3. So if you just arrange this equation, it will turn into W turbine out is equal to H3 minus H4. Okay, so because there will be a minus term over there. Okay, so then coming towards the condenser section, which is number 4 and number 1. Okay, so if you are going to analyze your condenser section by using again energy analysis, you can easily find out that your Q out, okay, because okay, at the condenser one, you can see that. Okay, so as the condenser, you can see that the W is equal to 0. So this term is going to be 0, 1. Okay, so then only left terms will be Q out. Okay, and your enthalpy at exit minus enthalpy at inlet. Okay, so Q out is equal to H4 minus H1. So now all of the terms are available to you now to analyze your Rankine cycle in terms of your enthalpy. So what you have to do is just to find out the enthalpy's value, and you can easily find out your thermal efficiency. So here there will be thermal efficiency. Okay, so thermal efficiency is your W net over Q supplied. Okay, and which is equal to 1 minus Q out over Q in. Okay, so if you can just analyze 1 minus what is your enthalpy relation for your Q out, it's H3 minus H4 and Q in H2 minus H1, right? Okay, so now rearrange it and you will get this relation. Okay, so now in order to analyze our thermodynamic system for your Rankine cycle, what you have to do is you have to find the enthalpy at state 2, enthalpy at state 1, enthalpy at state 3, and enthalpy at state 4. Okay, so you can easily find out your thermal efficiency. Okay, there will be no problem. Okay, so now coming towards our okay, so now another important thing is how to find the enthalpy's values. Okay, so for the enthalpy's value, so in all our questions which are coming in the later lecture, you already have your P1, T1 and P2 is given in your questions. Okay, if these values are given, you can easily analyze your enthalpies at a different point. Okay, so how to find the enthalpy? If you see that your point 1, which is lies in your saturated vapor region, saturated vapor, so you need pressure 1, temperature 1 in order to find out enthalpy 1 and entropy 1. Okay, so for the state number 2, it lies in your saturated, it lies in your liquid and vapor region. Okay, two-phase region. Okay, so all of you know that for if your state is in two-phase, you have to find your values by using this relation. S2 is equal to S2F X into S2FG. Okay, so S2F is your saturated liquid. Okay, plus X is your quality, and S2FG is equal to SFG is defined as over Sg minus Sf. Okay, which means that your entropy at your gaseous state minus entropy at your fluids liquid state. Okay, and then if you okay, so if in the question the quantity is not given, so you have to find out from this relation first your quantity and then put that quantity in second equation. But if your quantity is already known in the question, then you can directly use this second equation, H2 is equal to H2F plus X into H2FG. So you can find the enthalpy value at state 2 as well. Now coming towards the state
सर ये
3.
पता कैसे चलेगा कि आइसेंट्रोपिक प्रोसेस है सर?
जी, आइसेंट्रोपिक प्रोसेस आपको पता होगा क्योंकि जब आपका क्वेश्चन आपके पास आएगा तो उसमें लिखा होगा there will be isentropic expansion, there will be isentropic compression. Okay, or if there will be a Rankine cycle, you always know that in the turbine there will be isentropic expansion. Okay.
Okay sir.
Okay, now coming towards state number 3. The state number 3 is your saturated liquid point. Okay, and you already know that pressure at 2 is equal to pressure at 3 because this is the constant pressure heat rejection process. Okay, so mean if your pressure number 2 is given in the question, you can find out the pressure number 3 as well. Okay, because these are the same. Then you can again go to your saturated water tables. Okay, and find out the enthalpy value for the saturated liquid one, that is HF and S3F. Okay, again coming towards the number 0.4. So 0.4, the pressure 1 is equal to pressure 4. Okay, so if your pressure 1 is given, you can easily find out the pressure 4 and you can easily find the enthalpy value at 0.4 as well. Okay, so here this is the way we can analyze it. I will just explain through one question as well. Okay, so after this question, you have to do one question by yourself as well. So listen to this question carefully. Okay, so first you have to read this question. This is your example number 10-1 from your book as well. So now coming towards the question. Okay, what does this question say is that consider a steam power plant. Okay, so first thing from the steam power plant, it's mean that this is your vapor power cycle. Okay, here one thing will be clear. Okay, and it will be operated on the Rankine cycle. Okay, it is written over there, ideal Rankine cycle. It's mean that there will be isentropic compression and isotropic expansion processes involved in it. Okay, if it is written that there will be ideal Rankine cycle. Okay, the steam enters the turbine at 3 megapascal and 350 degrees C. Mean your pressure T1 is given and temperature T1 is given to you, okay, in the question, and is condensed in the condenser at the pressure of 75 kilopascal. Okay, so where your condenser is at number 0.4, mean your 0.4 pressure is also given in the question, 75 kilopascal. So what does this question say is that you have to find the thermal efficiency of this cycle. Okay, so now what you have to do is again using the equations which we already derived from the energy balance equation, you have to find out different Q in, Q out, and your work done by your system, and then your Q supplied, and you can just divide it and find out the thermal efficiency. So now coming towards your analysis at state 1. Okay, so at the state 1, you already know the state 1, it will be pressure 1 is equal to 75 kilopascal. Okay, that was given in your question. So now you have to, what you have to do is go to your thermodynamics table. Okay, so this is your thermodynamics table. You already have familiarity with this type of tables. This is available at your end of the book. Okay, so now go towards table number saturated water. Okay, so now go towards the pressure table, which is table number A5, because your pressure is given. If in that point temperature is given, then you have to follow the table A4 because it will be in the form of temperature. But right now we are having a pressure, so we have to go towards saturated water pressure tables. Okay, so P1, okay, 75 kilopascal. You have to see 75 kilopascal over there. Okay, okay, so now you have to follow this line in order to find out your enthalpy value. So H1 is equal to HF. So where your HF is? HF is equal to 384.44. Okay, kilojoule per kg. So now your H1 is known. Okay. Now again you have to find out specific volume. Okay, specific volume at 1 is equal to saturated liquid 1. So where your saturated liquid specific volume, which is your VF value. So 0.001037. So means your specific volume at 1 is also known to you. Okay, so here is this one. Okay, so H1, V1 is known to you by your thermodynamics table. Now coming towards state number 2. Okay, so state number 2 is an isentropic process. Okay, as you know that P2 is already known to you, that is 3 megapascal. Okay, so you can find out, first thing is you have to find out the enthalpy value at state number 2. Okay, so first we have the relation W pump in specific volume in P2 minus P1. So P2 is already given in your example, in your question. P1 is already given in your example. Specific volume at 1 you have find out just previously, okay, from thermodynamics table. So just put all the values in, you can easily find the pumping. Okay, so now we already know there will be a relation that W pump in is equal to H2 minus H1. So now you can have H1 as well. You have already find W pump right now, and you can easily find your enthalpy value at state 2. Okay, by putting all these value in this equation. Okay, so till now there will be a question. Any question? Okay, so now going towards the third state. Okay,
सर
so G.
सर ये स्टेट 2 पे एंट्रोपीज इक्वल हो गई हैं
जी
वो
स्टेट
भी
2 पे एंथैल्पी इक्वल है आपकी, ये देखें ना आपके पास आइसेंट्रोपिक कंप्रेशन प्रोसेस है ना ये. सो S1 इज इक्वल टू S2. क्लियर?
यस सर
Okay, so now coming towards state number 3. Okay, so your state number 3 is in your saturated which region? It will be in the saturated vapor region. Okay, so for saturated vapor region you have to find the enthalpies, but you need two properties: pressure at 3 and temperature at 3. So this is given in your question as well. Okay, so how to find the thermodynamic properties for the saturated vapor region? Okay, superheated vapor region. Sorry. So superheated vapor region, you have to follow again your thermodynamics table. Okay, so superheated is also okay. So this is your table number A6, which is superheated vapor, superheated water. Okay, so for superheated water, what you have to do is, for example, first thing is your pressure number 3 is given, which is 3 megapascal. So find out where your 3 megapascal is. Okay, so your 3 megapascal is over there. Okay, so here it's come that so this is your 3 megapascal. Okay, so we just have to find out 3 megapascal. Then your temperature is given, which is 350 Celsius. Okay, mean your pressure is also given, your temperature is also given. So now you have to just look for the values of enthalpies. Okay, so this is your value of enthalpy 3116.1. So this is your value at H3. Similar that you have to find the entropy value at H3 or point number 3 as well. So S3 is equal to 6.7450. Okay, so now your point number 3, state number 3, you have find out the values of your enthalpy as well and entropy as well. So now we have only left with the one state, which is state number 4. We already know that state 4 has 75 kilopascal, and the entropy value is, because this is isentropic expansion process, so S3 is equal to S4. Okay, so it's mean you have to find out the first quality S4, because this is your two-phase region, because point number 4 lies in liquid plus vapor region, mean two-phase, and for two-phase you have to follow this equation first. So S4 is known to you. Okay, S4 is known to you from, because it is similar to S3, SF. Okay, so where you can find out the SF value and SFG. So again you have to follow the thermodynamics table. Okay, so going towards the thermodynamic table again. Okay, going towards the saturated water. Okay, for the pressure table. So again you have to see that there will be a 75 kilopascal is your pressure. Okay, so you have to find out SF value. So where is your SF value? Okay, SF value is your this one 1.2132. Okay, so this is your SF value, and where is the SFG? Okay, 6.2426. Okay, so now your values are given. So here is these values. So 1.2132 and 6.426. Now put all these values and you can easily find out your quality. Once the quality is known to you, you just simply put again in this equation H4 is equal to HF plus H4 HFG. Okay, and you can find out the values of your enthalpy at point number 4. Okay, so HF is also coming from the same table. Okay, again you can just follow the 75 kilopascal line and you can just find out HF and HFG from the table from saturated water one from the pressure table. Okay, so now all the enthalpies, H1 is known, H2 is known, H3 is known, H4 is known to us. Okay, so now you just have to put in the equation which we have already derived from energy balance. Q in is equal to H3 minus H2. You can find out Q in value. Q out is equal to H4 minus H1. H4 is known to you, H1 is known to you. You can easily find out the heat output, okay, which is the heat rejected. And then in order to find the thermal efficiency, 1 minus Q out over Q in. So now Q out is given to you, Q in is equal to given to you, Q out is given to you. Now just simply divide it and you can easily find out the efficiency from here. Okay, so in this way you can easily find the efficiency of the Rankine cycle. So now another point is sometime in the question it was asked that you have to compare the thermal efficiency that you have already find out from your Rankine cycle and compare it with the Carnot cycle efficiency. So how to do that? Okay, so in when you come across such type of question, so just you have to follow one thing. So you already know that your Carnot cycle efficiency was defined as T minimum over T max, 1 minus T minimum over T maximum. So your T maximum is already known to you. Okay, so where does T minimum come from? Okay, so this T minimum come from your thermodynamics table as well. Okay, so from 75 kilopascal, the 91.76 is your temperature, saturated temperature. So just put that 91.76 in this one and you can find out your thermal efficiency from the Carnot cycle. Then you can compare your Carnot cycle efficiency with the Rankine cycle. Okay, so this is how you have to find out all the values. So till now there will be any question?